I've been studying machine learning recently, and I thought we might do a video or two on that topic on the channel. And as you can see, we're going to be using Visual Studio Code. The reason for that is basically I want to use a Jupyter notebook, and the experience is just best in Visual Studio Code. I can get my Vim key bindings more or less, and the full Jupyter notebook experience. So I found a dataset on brain tumors on Kaggle. So let's start by importing some stuff here. And take a look at the data. So I know we'll need this kind of stuff. No matter what. So let's get that running. Let's see if it works. Okay, we're also going to need this. All right, so let's load up a couple of examples. So let's call it no example, and it's going to be image open. And you know what we can do? We can go ahead and take a look here, and maybe also in this folder. All right. So let's try to load no 10 node JPEG, and we can try to show that. So it looks like this. And let's actually just make two images side by side. And it's going to be that one, and it's going to be this one. And cool, let's do yes 25. They have a different naming scheme in there, which is great. So you can see the images kind of look like this. And let's start by loading up the dataset. So first of all, I like to make some titles here. So let's call it classifier for brain tumor detection. And here we can say dataset. All right, so we need a data set, and in Pytorch we can define our own dataset class, but then we'll need some stuff here. So I think it's torch, utils, data, and later we also want a data loader, so we can import that. And then we can say here, let's just call it for now, let's call it brain image. Brain dataset, why not? And it's gonna inherit from this guy, and we are going to do some stuff. So we need a length. It needs to implement a length, and it needs to implement a get item, which takes an index. And to do that, I actually also want a path, because then we can say no images, those are the ones that are inside the no folder. And basically you can see up here that we have some JPEGs, we have JPGs, JP with capital J, and also JPEG. So I think we're just gonna try to get everything. That should work. And then this can be, sorry, we also need the yes images. So the full length of the dataset will be both of those together. And what we can do when we get an item is we can kind of alternate between these two. Let's say that. So let's say get yes is idx. So even numbers we get a yes, and odd numbers we get a no example. No, I don't think that's going to work very well. Let's instead say if index is less than, well, you know what? Well, we kind of need this information anyway. So if it's this, then we are going to get image path as the corresponding one in here, and else we're going to get it from here, from the yes images. And then we should also say positive sample. Let's call it positive. And this one's true. Then we need to load the image. So we're going to say image open image path. And then we should apply some transforms. So we get a tensor that has like a uniform size. You can see here they don't have exactly the same size. We want to scale everything to have the same size and so on. So later we're going to define a transform. So then we can return the tensor and whether this is true or false. So actually let's do 1, because normally you want numbers, not booleans. So let's do 1 and 0. And then this is going to be transform is going to be a composition of a bunch of things. So first we want to tensor, then we want to resize it, and I think we want to resize it to, let's make it quite small to begin with, and maybe we even want to normalize it. So we can normalize it like this, I think. So we define a class. Let's check that it actually works. We can do this. We cannot do that because this thing has to be, I think we can check it. How do we check? Okay, I don't know how to do that. It says Control K, Control I, but that didn't really work. Okay. Anyway, I think maybe we do this. This is how you do it. It has to be kind of an iterable. And that also did not work. Because I didn't make it iterable. It has to be actually a tuple. So let's do that. And now it's running. Okay. So let's get one example out. So you see we have a tensor and we have a number. And that means we can do something like this. Let's call it a label. And then we can just to make sure everything is all right, let's try to show it. And it's not gonna work because the shape is wrong, so we have to do this. And okay, we can get an image out, and you can see it's quite downscaled. It's kind of pixelated now, but that is fine. All right, so when you do machine learning, typically it's a good idea to make a simple baseline model so you can see whether building a huge neural network is even worth it, or you're just wasting compute power. So one thing you notice when you look at these two images is that this one with the tumor has much more brightness. So let's make a simple model that calculates like the average brightness. And then, you know what? So let's do something even before that. So let's say let's call it dataset investigation. And here we are going to calculate the average intensity value for all of the images, and then we're gonna plot it. So let's call it the mean values. So we can take the mean of the image, and I think we have to say item to get the number out for image, and label in the dataset. And then we can make a histogram of that and show that. All right. So let's do something else. So we can compare the negative means with the positive means. So I want to make it a little bit transparent. And here we're going to say no, here we're going to say yes, and let's do that. And now it's hard to see what is going on, so let's say label is all, here the label is no, and here the label is yes. And then we have to tell it to actually show us that. Okay, so you can see it's not completely wrong, like the mean intensity is kind of the yes case kind of shifted a little bit. There's a huge overlap and so on, so we'll get some false negatives and false positives, but that's all right. So I think as a cutoff we can choose like 0.6 or 0.5, 0.55, something like that. Like, so we hit this point here where the no distribution starts to go to 0 and the yes distribution is kind of peaking. So let's do that for the baseline. And I think it would be nice to have it as a class. And it's just gonna have a function called predict, which takes an image, and it says mean intensity, and now I think we don't want to do this, so let's just return mean intensity is greater than 0.55. And let's try to run that on a couple of examples. So let's say baseline predictions is the baseline model predict on the image, for image and label in dataset. Okay, so it worked, which is good, but it doesn't tell us a lot. Let's make an evaluation function. So I'm gonna make yet another section here, and it's just gonna take something which we'll call a model, and it'll also take a data set, and then we'll say total correct, and no correct, and yes correct. So we'll get these three numbers out. And then we'll say for image label dataset, we can say the prediction is the model run on the image. And then we're going to say it's correct if the prediction, and actually it should be turned into a floating point number. So if the prediction is equal to the label, it's correct. So then we can say total correct is this. And if the label is this, then we can say no correct plus equals this, and else is correct. All right. And then in the end, let's return the percentages instead. So let's say total correct divided by the length of the dataset, and the same for no correct and yes correct. And then let's run that on the baseline and the dataset. And let's see what we get out. So something went wrong, I think. Something definitely went wrong. Let's print a couple of these things. And then here we can just break. So here the label and the prediction are both they are both 0, but still it says that because I never. So let's put that one down there, and that seems correct. So the prediction is always because I have the wrong sign, it has to be like that. Okay, that makes sense. And now we can see, okay, we are correct in 70% of the cases. Of the ones where, and actually it should not be the length of the data set, we should also have no count and yes count. So, sorry, no count and yes count. And let's do that. Okay, so we're correct in about 70% cases all the time. So 30% of the cases where there's no tumor, we will predict there is a tumor, so 30% false positives. Or, no, that's probably not how you count it, but anyway. And then 70% correct in the yes case as well. So we get, the baseline is like 70%. It's not too bad, but we can probably do better. So it is an image problem. We have these images, so it means we could use something like convolutional net, but let's start with just a basic feed forward network. So let's call it basic feed forward. So I don't know what to call it, but we actually need some extra imports. So we need from torch, port neural network, and might also be nice to have this one. And let's go here. So we need to make it a module. And in the init function, we have to do this kind of stuff. And then we can actually do something kind of nice. We can set up the network as this sequential module. I think that's, if you're not doing anything too crazy, this is the easiest way to write it. So let's think about the input dimension. So input dimension is 1 by 64 because we resized it to 64 by 64. So let's go ahead and encode that like this. So first we need to flatten the image. So we'll use this flatten module. So it's a vector instead of an image. And then we can do some linear layers. So input dimension, and then maybe we want 2 times input dimension. Then let's do leaky value, like that. Then let's do another layer, and let's actually have that be the final one. We do need another activation function so that the output is between 0 and 1. So basically the only constraints are that the input dimension is this thing and the output dimension is 1, and also output values are between 0 and 1. Because we are predicting a kind of a probability that the image has a tumor. So now we can just run the network on the image, and that will produce prediction. Okay. Actually, we also need this prediction. So I'm going to take an image, and I wonder how we should do that. Because what the network does is returns probability, but if we want to make a prediction, we have to kind of make a cutoff and say, if the probability is higher than this, then we say it's a tumor or not. So we should actually do something like this. So let's run that through there, test that it's greater than the threshold, and then we will return it as a float because that's how we like to do it. All right, so let's train it. So we need a model, we need a data set, and we need an optimizer. So it will optimize these parameters. The learning rate will be something like this. We can probably get away with. And actually here we kind of want a data loader instead. So we get, let me do it like this. So we get an image batch and a label batch, let's say. And we probably also want how many times are we going to run through the data set. So for epoch, number of epochs, let's run through every single batch. Let's say the predictions is the model running the batch. What is the loss function? Good question. That should probably be binary cross entropy. Basically, if you do a prediction classification problem with a binary variable, you do binary cross entropy. And otherwise, it's probably just cross entropy loss. So anyway, the loss is the loss function on the predictions versus the label batch. And then we want to say, set the gradient, the current gradient to 0, calculate the gradients, and update the parameters. Let's also keep track of the epoch loss, and here we'll say epoch loss is plus equal to loss, but we can do .item to get the number out, I think. Let's try that. And then we'll say epoch plus 1 out of number of epochs has a loss of this thing, and we'll just give it 8 digits like that. And one more thing is we need to put it into training mode, the model, and let's also put it on the GPU. All right, so first we need a data loader. So I'm actually going to put that up here in the data set. So let's say data loader is this data loader thing. It's on the data set. The batch size should be, we don't have that many images, right? Let's actually do something like this. We only have 253 images, so the data loader is going to be the data set. Let's do a batch size of like 8 or 16, and we do want to kind of shuffle it. We actually, you know what we should do? We should do train test split. So for that, it's not called train, it's called random split. So let's go ahead and say that the training, this is the full data set, that's fine. Let's go ahead and say the train set and the test set is, and my Visual Studio Code has started to lag like crazy. It's a random split of the data set, and we'll say test percentage, because we have so few data points, let's say it's only 10%. So then train length is the length of the data set. Oh, why do we calculate it like that? Let's say the test. That's the test percentage, but probably we should turn this into an integer. And the train length is the length of the data set minus the test length. All right, so we do that, and I think we have to say train length, test length. All right, and let's have a look at the length of these guys. So that looks fine. So let's do the data loader. Sure, that's over the training set, and there we go. So now we have this, and we can go ahead and run it on the data loader. And let's do this. So we don't have the model actually. Let's define that in a different cell. So we're going to call it baseline model. It's just the baseline. And here, of course, we need to say baseline. So let's see if we can run that. And for some reason, it's called FF. So we shouldn't call it this, we should just call it FF model, I guess. And here, FF model. And now it seems to be running. And that did not work. Okay, that's because the model is on the GPU, but the images are not. And the labels are not. And that's very interesting. So some of these some of these images have colors, like it looks like, because there's 3 here, so that's great. So to handle that, I think we should do this to make sure that it's grayscale all the time. And to check that it works, let's restart and run all cells. Yes, restart. And now it seems to be, no, it doesn't. Target size, that's different than the input size. Okay, that is very interesting. So it seems that, let's do something else as well. Let's go ahead and enumerate. We'll say running batch this out of this. Yeah, so it fails immediately, which is what I expected. Okay, so there's something wrong, and what's wrong is that but it's also a bit weird. So maybe I think the problem is in the data set. We're kind of we're returning a number, which is kind of wrong. We should actually return a tensor for it to be kind of consistent within. So let's restart and run everything again. And should go here. Okay, now it's just training like crazy. The loss is pretty big, which is concerning. That is kind of weird. I didn't expect it to be so bad. And it's also not really improving. Let's train it for just a few more epochs like I would expect it to actually improve. Once that is done, we can try to evaluate it in the same way as we did here. We're using a specific threshold, so maybe that's not entirely correct. And we can evaluate it on the test set and also on the training set. Alright, so it's finished training. Let's try to evaluate it. And that also didn't work because inside the evaluate function we are kind of expecting the model to be on the CPU. So let's do this. Means the baseline kind of has to mock that. So it doesn't do anything, it's always on the CPU. So actually we can do here, we can assert device equals CPU, so we don't do anything weird. This still runs, yes. Numbers changed a bit, which is weird, probably because we changed it to grayscale, all of the images. So let's evaluate this thing. And okay, that's interesting. The loss, why is the loss so huge? Maybe I think let's divide this by the length of the data set. The length of data loader maybe. And then when we run it, we'll see that. And I reinitialized the model, so it's not that amazing, but okay. So on the training set, it has a horrible accuracy on the true cases, and so let's actually count how many are true, how many are false. So let's say sum 1 for so for some image and a label in the training set, if the label is equal to 0, and we'll do the same if the label is equal to 1 for the yes, and then let's print them. So it doesn't look too bad. Actually, you would expect it to probably be a little bit better at the yes cases. And now let's substitute train for test. And let's have a look at that. So it's also roughly balanced. And what did we do in the prediction? We did say if it's higher than the threshold. And in the data set, we do have, if we return a yes image, then, and this thing I want to call label now. So it's a little bit more easy to understand. So that's very interesting. Let's try to make this model a little bit more complicated, like this. And here maybe we'll have a couple of more dimensions like this. So now it's kind of a big model. Let's also print how many parameters are in this model. Number of elements for P and FF model parameters. There we go. And maybe we divide it by 1,000,000, so we see kind of like how that is way too many. I don't want 167 million parameters. What is 64 squared actually? It's 4,000. That's already a lot. That is already quite a lot. What if we do this? And we get 50 million. Still it's too many, I think. It's way too many. Let's try this. 16 million. Which is kind of crazy. It's kind of crazy. Surprised it actually trains that fast. Is the number, does the number seem correct? So, you know, this one was 4096. So we should have roughly this squared times, or rather plus that, which doesn't really matter. So we also get 16 million, right? Yeah. Okay. Let's evaluate again, just for fun. These two, maybe I do want those, just not here. Let's put them here where we actually define the data set. So that one goes there. That one also goes there. Those cells. Okay, now it ended up something completely different. So I think it's just not really training. It's not really learning anything. Let's drastically reduce the number of parameters. So now we have like, what is that, 80,000? I think that's a little bit better. Still, it's not really learning anything. So it could just be that it's not able to learn this type of model. So let's try with a convolutional network. So let's call it convolutional model. And again, we need to call this to hook up to the Pytorch magic. And we'll have the same, we'll do a threshold of 0.5. That doesn't really matter so much right now. We can tune that. And then here we'll say forward on the image is this thing, which we return. Okay. So when you do convolutional networks, you have to make sure that the sizes and things of the image works. So I'm going to pull out a test image and a test model, which will be this thing. And I'm going to run that through the model. And then we're going to print the output test shape. Actually, I don't need print. Let me make a few extra cells so I can actually center on this thing. So let's make the first layer. So it's called convolutional 2D. So the first input, the first argument is how many input channels are there. There's only one because it's grayscale. And then it's how many output channels we want. Let's say we want 32. Then we need the kernel size. We can do 3 by 3. Then we need the stride. We can do, let's try to do 1 for now. The padding is 0. And let's try that. So then we get this thing. What if we increase this? Then we don't lose any size. So let's make it 2. So the image is kind of halved. Let's actually add padding of 1, so it's exactly halved. All right, then I think we can do some kind of activation function. Let's just do a value this time. And then let's do a max pool. And like this. Let's see what happens if we do this. Then we're down to a 16 by 16 image. Maybe it's a bit too soon to downsize it so much. So let's get rid of that. And let's have another convolutional layer. 32, 64, kernel size 3, stride is 1, and padding is, let's do 0 for now. I think we need to set it to 1. And then we can do another value. And then let's do the max pool. So now we should have a 16 by 16. Let's do another one of these. So it's going to be 64. And I don't know, 64, let's do 64 again. Let's see what that gives us. And here we can set the stride to 2. So we're we're down to 8. Let's do it again. Let's do this kind of pattern. I don't know if that's good, but let's try it. So now we're down to 4. And how much is 64 times 4 times 4? That's only this. So when after this, we can actually go ahead and flatten it. Then we can run a linear layer from 64 times 64 times 4 times 4. And what was it again? It's like 1000, right? So let's do something like this. Let's do another activation. And let's finally bring it down to only one number, and then we are good to go. then we are good to go, I thought. So what happens here? Let's try just that. Ah, okay. So that's the problem. It's because it's kind of expecting us to input a batch. So let's go ahead and say 164. Let's pretend it's a batch, and now we get correctly out a number. All right. So that works. Let's also now see how many elements are inside. Like how big is this thing? So let's make it here. So convolutional model. And let's divide it by this. So it's about 10 times bigger than our feed-forward network, more or less. But let's try to train it. So we give the data loader, we run for 10 epochs. Let's see if that actually does anything. So it failed. Because I forgot that this thing has to be, the output has to be between 0 and 1, so we actually need this sigmoid function. New tensor. It's not clear to me what went wrong, but it fails here. I don't think it's like I don't really know why it should fail. Let's try to restart everything. Now it's gonna train this one again, but whatever. Okay, so I don't know, it got into some kind of weird state, but now it's running. So still it doesn't succeed in predicting anything, which is very weird. It makes me think that something is wrong. So how big was a batch? What did we say? We said a batch was 16. Okay. So let's try to plot a single batch. I think we can do this. Like that. So let's make it grayscale and then show it. And the data loader is not an iterator. Can we just do this? It's kind of weird. Shape. Right, it's because it's also there's also some labels so which we don't care about, so this should work. Looks correct to me, like doesn't look like anything is wrong. Let's actually get the labels now as well. And then we can do like label equals Yes, if actually let's not do it as a label, let's do it as a title. Okay. So that seems all right. Seems all right. But still the model is not learning anything. So I'm going to try to run it for a long time. Okay, I think I discovered something weird. You need to call sum on the loss function, even though it should do that by default. So let's see if I do that now. Now you can see the feed forward network actually learned something. You can see the error is kind of reducing. It's not perfect, but it's there. And if we run it, I actually want to change something. Let's just print a message. So what is the message? The message is total accuracy. It's going to be this thing, but only with 4 digits. And then I think we can actually do, there's kind of a weird thing also in C, but in Python. Where you can do this thing. So let's go ahead and get that in there. And actually it's probably not going to do what I want, so I think we need a new line anyway, sadly. Let's get that thing. And also only 4 digits. Then we're going to print the message and do nothing else. So when we evaluate this, it kind of prints some stuff. Now I do want to align it because I like that stuff. And now when we run this, it's a little bit easier to see. And we can start by writing train, and then here we can write test. So you can see it actually becomes quite good. Our baseline model had an accuracy of 70%-ish. This one, the linear model, goes up to 90. So that makes more sense. I would expect it to learn something, like not nothing. So you really need this, and it's so weird to me because if you look in the documentation, by default it should do that. But whatever. Let's try now this model, and we don't need this many epochs. Let's do 10 like the other one, so we get a fair comparison. And then we can just basically copy this. So let's start it running already. Let's get this one, convolutional. This one I don't want to look at anymore, so let's get rid of that. And it doesn't have anything called predict, which I forgot to do. So we want to return float self-net image greater than self-threshold. I think wasn't that the way we did it? Wasn't that the way we did it? Over here, and yes it was. So then we actually probably have to train it again. So it's also learning, it's a little bit more steady, I would say. And now it has a problem, which is kind of weird. because we just trained it on a bunch of stuff. The data loader also, I think it's because this thing doesn't produce batches. So we have to do 1, 1, 64, 64. Now this might not, okay, that one still worked, so that's nice. This should still work, and now when we run this, it still works. So it actually performs worse than the simple linear model. Could be because it has so many more parameters. So since it has 10 times more parameters, let's train it 10 times longer. Actually, let's make it fully fair. Let's say we reinstantiate the model, so it's from scratch. We trained it 10 times longer, and let's see what happens. All right, we trained it, and we get still poorer performance. Like, it's only a little bit better than the baseline, even though the loss is so low, which is kind of surprising. It is kind of surprising to me. That is actually very surprising. Because how can the error be so low if the reported accuracy is so low as well? It's probably because of this threshold thing. So we can try to set the threshold to something else. So yeah, so now it gets perfect accuracy. So basically it's so good that it will always produce almost 100% certainty on the results. And so obviously we should also try to investigate that here. It's kind of crazy it's so high, but at least this one gets 100%, which is kind of what I would expect. And it also generalizes way better than this model, even though it has a 90+% accuracy. When you go to the test set, it's poor. It's actually worse than the baseline. But this one is significantly better than the baseline. It's not amazing, like it's only 80%, but yeah, maybe if you train it more, you will see something. So I think that's gonna do it for now. I will find the link to the dataset, and then I will push this stuff to some repository. All right, see you in the next one. Bye bye.